All right, welcome, ladies and gentlemen, to 7.3. We're going to be finding the volumes of interesting shapes. You know how to find the volume of pyramids and cones and cylinders and spheres and all that sort of stuff. But what if it comes down to a shape that you don't know the formula for? Well, here's where calculus helps you. Calculus actually tells us that the volume is actually an integral of the cross-sectional areas. So let's take a look at what this is going to mean. So the volume of solid just meaning anything. It could be the volume of a bottle if you knew the equation for the bottle, or the side of the bottle. The volume of a solid is of known integrable cross-section. So if you had a cross-section and you knew how to find the area of that cross-section with some formula from A to B, that means we can take the integral from A to B of our function. So the integral from A to B of our area function with respect to x dx is equal to volume. And that actually ends up being a very simple formula. We already found that area was the integral of a line. Well, it kind of makes sense that volume would be the integral of area, kind of going in a backwards fashion there. So here's what we're going to do. We're going to find the area function of the cross-section of the figure. We're then going to find the limits of integration, and we are going to integrate and find the volume. So let's take a look at a relatively simple problem. I am using the textbook examples, but obviously I'm just going to be explaining them. So their pictures are going to be a lot better than mine. So let's see, if we were given a XY axis, and get rid of that little silly thing, and we drew a pyramid from the origin this direction and just bear with me here as I draw my pyramid. Ooh, look at those straight lines. All right, we're given that this pyramid is 3 meters tall. So at the base on the x-axis, that's 3. It also tells me that the width is 3 and 3 across the base. Now, we could obviously find the area or the volume of this pyramid very simply using our volume formula for a pyramid, but that's not what we want to do right now. What we actually want to do is we want to think about this in context of a calculus problem. So if we were to take a cross section right in here somewhere, this cross section is a square, and it has side lengths of x and x. And I know it's a square because it tells me the cross section parallel to the base is a square. And that should actually be pretty straightforward from our definition. Well, the area of this square is x times x. So that means my area equation is x squared. That's good because now I can look at my integral of x squared dx. Now I didn't find my area or my limits of integration yet, so let's go ahead and find that. The limits of integration, x can be anything from 0 to 3. That's as big as x can get. Oh, so that's straightforward there. And if we were to figure this particular function out, or this integral out, this would be x to the third over 3 from 0 to 3, which is 3 to the third power, 27 over 3 minus 0 over 3, which is 9 meters squared, by the way, because there are units in this problem. And that's it. Or sorry, not squared, cubed. 9 meters cubed, because it's volume. And that actually is the volume of that pyramid, because the pyramid is found by doing 1/3 times the area of the base times the height. Well, in this case, the area of the base is 9 times the height of 3 gets 27/3, which, oh, that's 9. Well, that's good that they matched, because they better match. But let's get into something a little bit more interesting. What if our cross sections were not squares, but they were circles? So it's a good idea to know that a circle is obviously, oops, sorry, not a of x. Let me get rid of that. That's silly. It is pi r squared. That's obvious. We should know that. So let's say we had the region bounded between the x-axis and 2 plus x cosine x. So here we go. We have our x-axis, or our y-axis, our x-axis. We have the function x plus 2 cosine x, which looks something like that. And between -2 and 2. So we're looking at this thing here. It's a much more interesting shape. And then if we were to rotate this around the x-axis, this would create a solid that looks a little bit like a vase. And I would use the picture from the textbook if I were you, if you wanted to see what that would look like. But we could take cross sections, and the cross section right here, let me use a different color here. The cross section right here would actually end up being a circle. So we could take the integral of a circle, so pi r squared dx. And in the x direction, x can only go from -2 to 2. But here's a problem. This is r squared. Well, r is not x. So we need to figure out what is the radius of this circle as it pertains to x. Well, it just so happens, by definition of a function, that's just distance away from the x-axis. Well, the distance away from the x-axis is my equation. So because pi is a number, I'm going to take this out in front. So this becomes pi times the integral from -2 to 2 of my radius, which is 2 plus x cosine x squared dx. And then we do a little bit of Math 9, and Math 9 tells me this should come out to about 52.43 units cubed. Did that backwards? Excuse me. And hey, there we go. That means if you could figure out the equation of the side of a water bottle, or the side of a vase, or some interesting shape, you could actually figure out the volume of that particular shape. And that's actually something we're going to be doing. That's our volume activity that we're going to do a little bit later. But let's take a look at some other stuff here. What about a washer cross section? A washer, not a washing machine. A washer looks like this, the stuff mechanics use and builders use. Okay, a washer looks like this, where this is the stuff and the middle is empty. Well, you could think of this as the washer cross section would be, well, the big washer would be pi r squared, so you'd have a big R. There's big R. Well, that would be the whole thing, but we have to take away the little r, or the little circle, which would be pi times little r squared. So there's little r, which we could then write as pi times big radius squared minus little radius squared. And that would actually figure things out. We can actually use these r's as functions of x here in a minute. So this is a washer cross section. Very simple. And what the problem we're going to be looking at is the region in the first quadrant enclosed by the y-axis and the graphs of cosine x and sine of x. Now, here we go. Here we go. If we look at the function sine of x, it goes like this. And if we look at the function cosine of x, it goes like this. And they intersect here at, if you remember, pi over 4, because they're the same point at pi over 4. And if you were to rotate this around the x-axis, you would in fact get washers. Very different sized washers. Obviously, way out here at the end, it's very big empty space, whereas as you get closer to the middle, it's a very small empty space, a much bigger enclosed space. But the big radius, big R, would be the largest distance from the x-axis, which is cosine x, and little r is the smallest distance from the x-axis, which is sine of x, which means my integral is now of the function pi, since it's a number, I take it out front, times big radius squared minus little radius squared dx. You need to figure out the area of or the limits of integration. Well, that's just the x direction, so it's from 0 to pi fourths. The book likes to do trig identities for us, by the way, so in case you're wondering. Cosine squared minus sine squared is actually cosine of 2x, which actually makes the integral a lot easier. Because the integral becomes pi times, let's say, sine x over 2 from 0 to pi fourths. Sine of pi fourths is, what, root 2 over 2. Oops, sorry, 2x. Lost my 2x. Goodness gracious. Sine of 2x over 2. Pi fourths, that becomes pi halves. Sine of pi halves is 1, so it becomes 1 over 2 times pi, which is pi over 2, minus, plugging in 0 just makes this 0, so my answer is pi halves units cubed. That's pretty cool. I like that problem. I like these problems. These are, I think they're kind of fun. What about this one? There's another type of way to solve this problem, and this has to do with cylindrical shells. So you have to remember that the volume of a cylinder is, I guess volume, is pi r squared h. But this works a little bit differently than just pi r squared h, because that would be just the volume of a cylinder. But we need to be able to integrate it. So we're actually looking at an area, and actually going to be a rectangular area. That's kind of weird. It's a rectangular area where it's actually pi times r times h. The height of my cylinder times the radius of my cylinder makes it a rectangle, and then that rectangle being rotated around actually creates a cylinder. So the region of the curve with the curve x to the 1/2, or radical x, by the way, x-axis and the line x equals 4. So here we have the, here we have the square root of x. Here we have the line x equals 4. You should probably know that they intersect at the point 4, 2. And here's what this particular method does. We take and we draw a line horizontal or parallel to the axis of rotation. And this is the kind of the hard part to understand this. The length of this line, the length of this line is actually, oops, let's not draw it that way. Let's draw it this way. 4 minus y squared. Because notice we're going in this direction where if you tilt your head, it looks like a quadratic in the direction of y. So this equation is actually x equals y squared. So now we're thinking about that other direction there, right, with respect to y. So this is actually the equation x equals y squared. And then the radius there, so this goes up to 2, by the way. The radius here is just the change in y, so it's whatever y is. So what we can think about is the integral of pi times the radius of the cylinder. This is actually going to be the cylinder right here. Ooh, that's ugly. That's the radius of the cylinder. The cylinder is going to be that y value times the height of that cylinder, which is 4 minus y squared, dy. So notice we're in the y direction and not the x direction. And since we're in the y direction, it goes from 0 to 2. Now, technically, you could do this in the x direction, but they want to show you every single type of way to solve this problem. Going through the math, which is not difficult, but to save a little bit of time, it's done for us already. This becomes 8 pi units cubed. Okay, last example here. And yes, it's kind of another type, but in this case, it's not a revolution. It's not a revolution solid, so we're not revolving around anything. So we have this paperweight. It's made such that the base of the shape is shaped like the region of the area between the x-axis and one arch of the curve, 2 sine x. Well, 2 sine x looks like this. From 2 going from 0 to pi. Well, that's that. But that's just the base of this shape. Now here's the challenging piece, trying to draw this thing. And I'm going to try to do my best drawing it how the book has it. It has the thing here. That's the base of the shape. But each cross section of this shape, so if there's a cross section drawn right here, or cut right there, it's actually a semicircle, or half a circle. And this cross section here is half a circle. This cross section here is half a circle. You notice these circles would actually get pretty big or small depending on how close they are to these endpoints. And there we go. We have a whole bunch of cross sections, with cross sections being semicircles. So we need to figure out how to find the areas of those. Well, how would we find the areas? Well, this is a semicircle, which means we can use some circle ideas here. But in order to do a circle idea, we need to excuse me. We need to figure out how to find the radius of the circle. Okay, well, the radius of the circle is half of the function 2 sine x, because the function being the full distance, the diameter, it actually says that, the semicircle whose diameter runs from the x-axis to the curve, which means the radius is just half of that, which is equal to sine x. So therefore, the area of each of these circles, or semicircles, since they're semicircles, that just means they're half of pi times r squared And that means we now have a function. We now have a function of area, so we can find the integral. Half times pi is just a number, so we're going to take pi halves out to the front. And we're going to say sine squared x dx. We need to figure out our limits of integration. And in this case, x goes from 0 to pi. We do a little bit of math. Our calculations, either by hand or by calculator, whatever you end up doing, is going to be pi halves times 1.57. That's interesting because that kind of looks like pi halves. It is pi halves. If you did the math by hand, you'll probably get pi halves. Oops. If you did it math 9, it's kind of a cool area, pi squared over 4. You could get the decimal approximation. If you did this with math 9, this thing right here comes out as 1.570 blah, 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 blah. Oops, where'd my 5 go? 1.57079 blah, 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 blah. And if you see the number 1.57, you should probably check to see if this was actually pi over 2. Just because it actually ends up being pi over 2. So you get this as the volume. So in this particular case, I didn't write it, but we're dealing with inches. So the volume of this shape is pi squared over 4 inches cubed. It came out to about 2.47. All right, I'm going to leave you guys with that, and I will see you guys tomorrow.